What if I told you there is a place in the universe where time itself comes to a halt? A place where the laws of physics as we know them cease to apply. Imagine a journey from which there is no return, not even for light. This is not science fiction. This is the reality of a black hole. It promises answers to some of the deepest questions about our cosmos. A one-way trip, a voyage into the ultimate unknown, a plunge into the heart of an enigma wrapped in the fabric of space-time. The experience would be unlike anything in human history. Our story begins right here, in your imagination. Picture yourself in a small spacecraft, drifting through the silent cold of deep space. You are an explorer, far beyond the lights of our solar system. Stars like brilliant, unblinking diamonds. Then you see it, a patch of darkness, a perfect circle of nothingness swallowing starlight. This is your destination. You have arrived at the edge of a black hole. So, what exactly is this cosmic titan that you are approaching? In the simplest terms, a black hole is a place where gravity has become overwhelmingly powerful. It is a region of space-time where the gravitational pull is so immense that nothing can escape its grasp. Not a planet, not a star, not even light, the fastest thing in the universe. This is why they are called black holes. They do not emit or reflect any light, making them invisible to our eyes and telescopes. We can only detect them by observing their effects on the matter and stars that orbit near them. To understand this immense gravity, think of a bowling ball placed on a stretched-out rubber sheet. The ball creates a dip, a curve in the sheet. Now imagine rolling a small marble nearby. The marble will follow the curve and circle around the bowling ball. Stars and planets warp the fabric of space-time, and other objects follow these curves. A black hole is like taking that bowling ball and squishing it down to the size of a tiny pebble. The mass is the same, but it is packed into an impossibly small space, creating an incredibly deep and steep well in the fabric of space-time. This extreme density is what gives a black hole its defining feature, the event horizon. Once you cross this invisible line, the gravitational pull becomes so strong that you would need to travel faster than the speed of light to escape. Since nothing can travel faster than light, escape is impossible. It is the ultimate one-way door in the universe. They are the final, dramatic act in the life of a truly massive star. In its core, a powerful process called nuclear fusion is taking place, releasing a tremendous amount of energy. When fusion fuel is exhausted, the outward pressure vanishes. Gravity wins. Then rebound in a titanic explosion, a supernova. Back in your spacecraft, the fall has begun. You have cut your engines, now you are in free fall, pulled silently toward the black hole. From this distance, the effects are subtle. The black hole is still a perfect circle of black against the stars. But something strange is happening to the light around it. Stars at the edge appear distorted, their light bent through curved space-time. This is gravitational lensing. The black hole acts like a massive magnifying glass, warping the view behind it. As you get closer, a more profound effect begins. It alters the very flow of time itself. For you inside the ship, time seems normal. The clock on your dashboard ticks the seconds one by one. From a safe distance, your journey appears to slow. This is time dilation. The stronger the gravity, the slower time passes. From outside, your ship seems to take longer to cover less distance. The light from the universe also changes. Stars behind you shift toward blue, compressed, higher energy. Look away. Your home galaxy reddens and stretches. The universe behind you fades and dims, receding. You become disconnected from the rest of creation. You try to send a message back home, a final report. For you, the transmission sends in an instant. For colleagues, the signal arrives stretched out. Your final words slow, drop to a low pitch, then fade into a silent hum. To the outside, you appear frozen at the edge, reddening and fading forever. You have become a ghost on the edge of forever. Around its edge, you might see a spectacular sight, an accretion disk, swirling, superheated gas and dust, debris from stars. Friction heats it to millions of degrees. It glows with incredible brilliance across the electromagnetic spectrum. A final, fiery halo before the darkness, chaotic and dangerous. Material moves at near the speed of light. The light would be blinding, the radiation lethal. Imagine we approach a dormant black hole without such a disk, a clearer, safer path, but the forces are the same. Tidal forces grow stronger with every kilometer you descend. Your ship is pulled more strongly on the side closer to the black hole than on the side farther away. This difference in gravitational pull is the key to what comes next. Imagine holding a rubber band. Pull one end more than the other. It stretches. The same principle applies to you and your ship. At first, the effect is minuscule, undetectable. As you get closer, the difference across your ship and body becomes immense. The atoms at your feet are pulled with far more force than the atoms at your head. The stretching has begun. This process is known, somewhat poetically, as spaghettification, playful and terrifyingly accurate. Tidal forces increase exponentially as you approach the event horizon. Your spacecraft will begin to groan and creak, its metal frame elongated and compressed. The very structure of your body is under assault from warped space-time. Not a collision with a solid object, but a gradient of gravity so steep, it will tear you apart. Atom by atom. The end comes quickly now. The tidal forces are no longer a subtle pressure, but an irresistible, violent force. Your body and everything around you is being pulled into a long, thin strand. This is spaghettification in its final terrifying stage. The force of gravity at your feet is now thousands or even millions of times stronger than the gravity at your head. The chemical bonds that hold your body together are no match for this cosmic tug of war. You are being stretched, elongated, and thinned out, like a piece of spaghetti being pulled from both ends. It is a process of complete and utter deconstruction. Your bones would snap, your muscles would tear, your body would be elongated into a thin stream of atoms, flowing down into the black hole. The same fate befalls your ship, the metal bulkheads, the control panels, the very chair you are sitting in. All of it is stretched and torn apart, forming a parallel stream of matter alongside your own. It is not a painful death in the conventional sense, as your nerve endings would be destroyed almost instantly. It is a fundamental unraveling of your physical form. For a smaller, stellar mass black hole, this process would happen before you even reach the event horizon. You would be torn apart before you ever had the chance to cross the boundary. However, for a supermassive black hole, the kind found at the center of galaxies, the story is different. Their event horizons are much larger, and the gravitational gradient is gentler at the edge. You could, in theory, cross the event horizon completely intact. Let us assume you are falling into a supermassive black hole. The tidal forces are gentle enough that you survive the crossing. One moment you are outside the event horizon, the next you are inside. For you, there is no grand explosion, no wall to crash through. You might not even notice the exact moment you have crossed the threshold. The fall simply continues. Before, you could have, with enough rocket power, turned around and escaped. Now, escape is no longer a possibility. All paths, all possible futures, now lead in only one direction. Forward, to the center. Looking back, you would not see the universe you left behind. Because you are now moving inward faster than light can travel outward, the light from the outside universe can no longer reach you. The view behind you would be one of absolute darkness. Looking forward, however, is a different story. The light that fell into the black hole before you, the light that is falling in with you, is all compressed into a single point ahead. You might see the entire history of that patch of the universe, from the black hole's formation to its distant future, flash before your eyes in an instant. Inside the event horizon, space and time swap roles in a way that is difficult to comprehend. In our normal lives, we can move freely in the three dimensions of space: forward, backward, left, right, up, down. But we are forced to move in only one direction in time, toward the future. Inside a black hole, this is reversed. The singularity, the center point, is no longer a place in space. It is a moment in time. It is your future. You can no more avoid hitting the singularity than you can avoid next Tuesday. Space itself is flowing inward, carrying you with it. Your perception of reality is now completely distorted. The laws of physics as you have always known them are breaking down around you. You are isolated from the rest of the cosmos, a solitary consciousness adrift in a bubble of warped space-time. There is no sending a message out. There is no turning back. The journey's end is now a certainty. The only thing that remains is the final, crushing destination, the singularity. What was once a journey through space has become a relentless march through time to a predetermined end. What lies at the very center of a black hole? Our current understanding of physics gives us a single, baffling answer: a singularity. This is a point of zero volume and infinite density, where gravity becomes infinitely strong and space-time curvature becomes infinite. Here, all the known laws of physics, including Einstein's general relativity, break down completely. To truly understand it, we would need a new theory, a theory of quantum gravity that can unite these two great pillars of modern physics. For a long time, it was thought that anything falling into a black hole was lost forever. The information that made up an object, its structure, its composition, was believed to be permanently destroyed. This created a problem for physicists. It violates a fundamental principle of quantum mechanics. Information can never be truly lost. The universe, it seems, should always keep a record. This puzzle is known as the black hole information paradox. But the work of Stephen Hawking offered a startling solution. Hawking proposed that black holes are not entirely black. He theorized that due to quantum effects near the event horizon, black holes should slowly emit a faint glow of particles. This process is now known as Hawking radiation. Over immense periods of time, this slow leak of energy causes the black hole to lose mass. It evaporates. The process is incredibly slow. A black hole the mass of our sun would take longer than the current age of the universe to evaporate completely. But it implies that black holes do not last forever. This raises a profound question. If a black hole evaporates, what happens to the information it consumed? Does it disappear along with the black hole? Or is it somehow encoded in the faint Hawking radiation that escapes? Scientists are still debating this. Some believe the information is scrambled and released. Others propose it is stored in some way we do not yet understand. The answer could revolutionize our understanding of gravity, information, the very nature of reality. It is one of the deepest mysteries in all of science. And so, our journey ends where it began, with a question. Black holes represent the limits of our knowledge. They are cosmic laboratories where the laws of nature are pushed to their absolute extremes. They challenge us to think of new theories, to imagine new possibilities for the universe. They remind us that for all we have discovered, there is still so much that remains unknown. The darkness of a black hole is not empty. It is filled with the promise of discovery, a silent testament to the vast, beautiful, enduring mysteries of the cosmos. This is not the end, only the edge of what we can yet imagine.